dry ether is used as a polar aprotic solvent. But when you take the terminal alkyne where the triple bond is present at the terminal carbons, so this is based on Friedel-Crafts reaction. Let's see. You have a benzene ring and this is the alkyl halide. Hello students, welcome to Ellen Overseas and welcome back to the very important series that we have started, that is 45 important topics in 45 days, that is especially dedicated to your JEE Main 2024 exam, right? And this series is divided into 3 parts, that is 15 topics from physics, 15 from chemistry, similarly 15 from mathematics, and I will be discussing this chemistry part, right? So let's continue this series with the next topic of chemistry, and that is important name reactions, and this is taken from the chapter hydrocarbons. Okay, so let's start this topic and let's see the first name reaction, that is Wurtz reaction. Okay, so what is Wurtz reaction? In Wurtz reaction, it is used for the preparation of higher alkanes containing even number of carbon atoms. Okay, this is very important. This is very important application of this reaction, that we are going to use this reaction for the preparation of higher alkane, and that too having even number of carbon atoms, right? And here dry ether is used as a polar aprotic solvent. Okay, so you can see this reaction here. You have methyl bromide. So basically in Wurtz reaction we take the alkyl halides, right? What we are going to take? We are going to take an alkyl halide, okay, and that will be reacted with the sodium metal in presence of dry ether, and then you can see that it is kind of a coupling reaction. 2 methyls have combined, have coupled together, and you are getting a higher alkane. So this is ethane, and that is higher alkane, okay, and with this you are getting NaBr, right? So higher alkanes are obtained by this reaction, right? Similarly we have the another method that is called as Kolbe's electrolysis method. So what happens in this method? Alkanes are formed on electrolysis of concentrated aqueous solution of sodium or potassium salt of saturated monocarboxylic acids. Okay, so first of all we have to take the salt of sodium or potassium salt of saturated monocarboxylic acids, and we have to make a concentrated solution of this salt, and then electrolysis of the salt will give us the higher alkane. So the very common thing about this reaction and Wurtz reaction is that we are going to get higher alkanes in both reactions. Okay, so suppose you have this sodium carboxylate salt. Okay, this is saturated monocarboxylic acid and salt of this carboxylic acid with sodium, right? And this is the aqueous solution and you are electrolyzing it, so you are getting RR. RR means higher alkane. Higher alkane plus CO2. CO2 gas will be obtained. Hydrogen gas will be obtained in NaOH. These are the products of Kolbe's electrolysis, and very important thing about this is that here the alkane and CO2, these are obtained at anode, and these two products, hydrogen gas and NaOH, are obtained at cathode. This is the important thing about this, right? So here also we are getting the higher alkane. That's why this is the note here that methane gas, methane cannot be produced from Wurtz reaction as well as from Kolbe's electrolysis, because methane is having only one carbon, but you can see that these two reactions are kind of coupling reaction where one alkyl group is combining with another alkyl group, similar alkyl group, and that's why we are getting the higher alkane. So the smallest alkane that we are going to get by these two methods will be ethane. Okay, so we cannot get methane from these methods, right? Now let's see the next. Methods of preparation of alkene. Now, if we talk about the alkene, then which important methods can be used to prepare the alkene? So, we have taken this important method, that is using alkynes. So, by partial hydrogenation of alkyne gives us alkene. Okay, partial hydrogenation means in alkyne you have 3 bonds, okay, 2 pi bonds. So only 1 pi bond will be broken, other pi bond will remain as it is. So only 1 pi bond is broken, 1 will remain as it is. That means alkyne will be converted to alkene. Okay, so first reagent that we are using here is palladium metal, hydrogen gas in presence of palladium metal on calcium carbonate in presence of quinoline. Okay, this reagent is called as Lindlar's catalyst. Okay, so in presence of this catalyst, what will happen? Cis alkene is formed here as a product. Okay, cis alkene will be formed. So if we make this structure, cis alkene is obtained because in presence of this reagent, the addition of hydrogen on these carbons takes place from the same side. Okay, that means syn addition takes place. That's why when hydrogens will remain at same side, so the other alkyl groups will also remain at the same side. So we can say that this is cis alkene, right? So this is the characteristic of this reaction and this reagent, that cis alkene will be obtained, right? Okay, so what is Lindlar's catalyst? Metallic palladium deposited on calcium carbonate conditioned with lead acetate and quinonyl. This is called as Lindlar's catalyst. Okay, so always remember, in presence of Lindlar's catalyst, you are going to get cis alkene from alkyne, right? This is one reaction. Now, second partial hydrogenation reaction is Wurtz reduction or using Wurtz reducing agent. Okay, this reaction is called as Wurtz reduction, and the reducing agent, the reagent that we are going to use is called as Wurtz reducing agent, that is sodium or lithium, the active, highly active metals in liquid ammonia. Okay, this is the reagent for this Wurtz reduction, right? So here you have the alkyne. Again, you have the hydrogen and sodium in liquid ammonia. So what is the characteristic of this Wurtz reduction? The characteristic of this Wurtz reduction is that here you are going to get trans alkene only. Okay, trans alkene will be the product of this reaction, because in this reaction the addition of hydrogen takes place from opposite sides. Okay, that's why you are going to get trans alkene. Okay, fine. So now what is the note here? This process of reduction is not eligible when terminal alkynes are taken. Okay, because terminal alkynes form sodium salt with sodium metal. Okay, so here this alkyne, if you see, this is non-terminal alkyne. Okay, non-terminal alkyne is converted to alkene. But when you take the terminal alkyne, where the triple bond is present at the terminal carbons, then what will happen? You know, this hydrogen present at this sp hybridized carbon is acidic in nature. That's why when this terminal alkyne is taken, it reacts with the sodium metal and forms the sodium salt. Here you can see the reaction. This is terminal alkyne reacting with the sodium metal in liquid ammonia and forming the salt here, forming the sodium salt here at the end of the reaction, right? So here you are not going to get any alkene, instead you are getting a salt, right? So this was the important point regarding this Wurtz reduction. Now let's see the next point. Here the next reaction, next very important reaction is ozonolysis. Okay, ozonolysis of alkenes. Okay, here you can see that you have an alkene, and ozonolysis means we are going to react this alkene with ozone in presence of zinc or water or H2O2. Okay, so what will happen? As the name is suggesting, ozonolysis means this ozone is going to break this compound. Okay, how? So basically when we talk about this reaction, ozones break the double bond and makes an intermediate which is called as ozonide. Okay, And ultimately what will happen? Ultimately, after completion of reaction, we will see that after breaking the double bond, one oxygen atom is added on each carbon, each double bonded carbon by double bond. Okay, these will be the final products. So if I make the products here, first product will be R1C double bond O and one hydrogen. This is the first product. Similarly, the second R2C double bond OH. So both are aldehydes, you can see. So whenever on the double bonded carbons, if you have hydrogens, at least one hydrogen, then you will get aldehydes only. Okay, so these are the aldehydes. Now what is the important point regarding this reaction? Let's see. If final product is oxidized by hydrogen peroxide H2O2, it is called as oxidative ozonolysis. Now instead of H2, if we use H2O2 here, okay, and instead of zinc, if we use the H2O2 here, then it will be called as oxidative ozonolysis, because these aldehydes will be oxidized by the H2O2 in carboxylic acids, respective carboxylic acids. Okay, so that will be called as oxidative ozonolysis, right? But in presence of zinc, when you have taken the zinc dust or dimethyl thioether, H2O2 cannot oxidize the carbonyl compound produced, and ozonolysis is called as reductive ozonolysis. So this reaction which is given here is basically the example of reductive ozonolysis, because here zinc is given. In presence of zinc or dimethyl thioether, the reductive ozonolysis will take place and the final products will be aldehyde and ketones. Whereas in oxidative ozonolysis, the final products are carboxylic acids and ketones. Okay, we know ketones are not easily oxidized, right? So let's see few examples of this ozonolysis reaction. So here you have the compound. You can see on both carbon atoms, you can see the hydrogens. So breaking the bond, adding oxygens. Okay, so what will be the products? First product will be CH3 C double bond OH, this one. Okay, acetaldehyde, and the other will be, here you have two hydrogens, so this will be formaldehyde. Okay, these are the products. Let's see the next. Okay, in this reaction you can see we have multiple double bonds, so each double bond will be broken. Okay, and we have to add one oxygen on each carbon from each side of double bond. Okay, fine. This is how the bonds will be broken. Now first of all, this first product R1 C double bond OH, this is the first product. Now look at the middle carbons, COO, CO2, COO, CO2, CO2. So we are getting 3 CO2 molecules from this compound. So 3 CO2 molecules, right? Now this one, this is also aldehyde R2 C double bond OH. This is also the aldehyde. This was R1. These are the products, right? Now let's see the next one. Here also you have multiple double bonds, so we have to break each double bond, adding oxygen atoms. Okay, and this double bond will also be broken. So ultimately we'll get okay. So here you are getting CHO. Okay, on this carbon also you are getting this aldehyde group. Here also you will get the aldehyde group. Okay, and these are the 2 CO2 molecules. So plus 2 CO2 plus this one will be formaldehyde, HC double bond OH. Okay, these are the products of this reactant, right? Now similarly, when you have benzene, when reductive ozonolysis of benzene is taking place, then what will happen? Here also all the 3 pi bonds will be broken and oxygens will be added on each carbon. Okay, so what we are going to get? This is broken in 3 parts. This whole ring is broken into 3 parts. So this part is this carbon, both are having 2 aldehyde groups. So basically we are getting this compound here, C double bond O, H, C double bond O, H. Okay, and the same we are getting 3 similar parts. Okay, so benzene will be broken into these 3 parts, and this is called as glyoxal. This is called as glyoxal. So we are getting 3 glyoxal molecules after reductive ozonolysis of benzene, right? So this is how ozonolysis reactions takes place. Fine. Now let's see the next reaction, that is Friedel-Crafts reaction, alkylation. Okay, this is also very important name reaction for the aromatic hydrocarbons, right? So Friedel-Crafts alkylation and Friedel-Crafts acylation, these are the 2 reactions. So let's see. When we talk about alkylation reaction, then electrophile is carbocation. And let me tell you, Friedel-Crafts reactions are ESR reactions. ESR means electrophilic substitution reaction. Basically, aromatic electrophilic substitution reaction. Okay. So here electrophile is carbocation. Reagents are RX. RX means we'll be taking the alkyl halide and Lewis acid. These are the reagents for this reaction. So you can see we have a benzene ring and this is the alkyl halide, Lewis acid, and we are heating. Then what we are going to get? We will get this product. Okay, alkylation of benzene will take place. This will be the product. Okay, so Friedel-Crafts acylation. This was alkylation where alkyl group has attached, and what will be the carbocation? Here carbocation will be R positive. This will be the carbocation. So aromatic electrophilic substitution reaction will take place. This R positive is going to reduce one hydrogen, is going to replace one hydrogen from the benzene ring. Okay. Similarly, you have acylation. So in acylation, what is the electrophile? Electrophile is acylium ion. This cation is called as acylium ion. So if we make the structure of this cation, this structure is like this. Okay. So this is the electrophile of this reaction, and the reaction will be called as Friedel-Crafts acylation, and this will be the product of this reaction. Similarly, here also aromatic electrophilic substitution reaction is taking place. So one hydrogen from the benzene will be replaced by this acylium ion, right? So this will be the final product. Now let's see what are the limitations of this reaction. So limitations of Friedel-Crafts reactions are, first of all, Friedel-Crafts reaction is not possible in presence of strong deactivating groups. Okay, that is all meta-directing groups. So first of all, Friedel-Crafts reaction will not take place when you have very strong deactivating groups. What are deactivating groups? Which are meta-directing, which withdraw the electron density from the benzene, like NO2, highly electron withdrawing cyanide, carboxylic acid, ester, sulfonic acid, R3, NR3 positive, aldehyde, ketone, etc. All these groups are highly deactivating in nature. So in presence of these groups, the Friedel-Crafts reaction is not possible. This is one limitation. Similarly, second limitation is Friedel-Crafts reaction aren't possible in presence of strongly activating groups. When you have highly activating groups also, then also Friedel-Crafts reaction is not possible. For example, O negative, NH2, or okay, all types of amines we can say, OH and OR. All these groups are highly activating in nature. So why this reaction does not take place in presence of these? Because in presence of these groups, Friedel-Crafts reaction is not possible because these groups make coordinate bond with the Lewis acid AlX3, and aromatic ring also becomes deactivated. Okay, so what will happen? Suppose if I take the example of phenol. Okay, so here you know that on oxygen you have 2 lone pairs. So we are taking one Lewis acid for this reaction. Suppose we are taking AlCl3. So this is a Lewis acid. So it will accept a pair of electron, and oxygen has the electron pair. So oxygen will donate a pair of electron to the aluminium, right? And one coordinate bond will be formed. So after this, what you will get? oxygen, AlCl3, this is the coordinate bond. This will gain a negative charge, positive, and hydrogen. Okay, so you can see due to positive charge on oxygen, this ring has become highly deactivated. Okay, so that's why now it will not show the Friedel-Crafts reaction. So these are the limitations of Friedel-Crafts reactions, right? Now let's see this question, what this question says. So this is based on Friedel-Crafts reaction. Let's see, you have a benzene ring and this is the alkyl halide here. So this is 1 degree alkyl halide, you can see. Okay, this is 1 degree alkyl halide, AlCl3 Lewis acid. So hydrocarbon X is the major product. So we have to identify the X. Okay, so here few options are given. So let's see. First of all, you have the 1 degree alkyl halide. So this will react with the AlCl3. So let's see. Okay, how many carbons do we have? Let's see. 1, 2, 3, 4 carbons. Okay, so CH3, CH2, CH2, CH2 and Cl. And on chlorine we have 3 lone pairs, right? And you have the Lewis acid AlCl3. So this chlorine is going to donate a pair of electron to the aluminium, right? After this donation, we know what will happen. This will take, after this chlorine will get the positive charge, this bond will be broken and this carbon chain, this carbon will gain a positive charge. Okay, so carbocation will be formed. So CH3, CH2, CH2, CH2 positive, this carbocation will be formed, plus AlCl4 negative. Right, now look at this carbocation. This carbocation is 1 degree carbocation. 1 degree carbocation, which is very less stable. So what will happen now? The rearrangement of carbocation will take place to make it more stable, right? So rearrangement will take place. Rearrangement of carbocation will take place. So what will happen? 1,2 hydride shift will be taking place. So we can write 1,2 hydride shift will be taking place here, right? So after this 1,2 hydride shift, what we will get? CH3, CH2, CH positive and CH3. So this is the 2 degree carbocation. 2 degree carbocation, which is more stable comparatively. More stable comparatively. And after this, more rearrangement is not possible, right? This is the most stable carbocation which we can get from this compound, right? 2 degree. So now this 2 degree more stable carbocation is going to attack on the benzene ring, and then aromatic electrophilic substitution reaction will take place. So we can see the product which is having this 2 degree carbocation. So here this cannot be the answer, you can see. This is not what we are getting. In the B, it is 3 degrees, so this is also not possible for this compound, right? In the C option, this is formed by 1 degree carbocation, so C is also incorrect. And in the D, you can see this product will be formed by the 2 degree. This was a 2 degree carbon, 2 degree carbocation. So yes, option D will be the right answer of this question. Okay, so this is how we can solve the questions related to Friedel-Crafts reactions, right? So that's it from my side on this topic. So we'll be continuing this series, so stay tuned with us. And if you have any query or suggestion, do share with us in the comment box. And don't forget to watch the complete series. The playlist link is given in the description box, right? So stay tuned with us. Thank you.